Okay, so if we look at these two things I have on the board up here, around the chirality center, I'm defining configuration, arrangement of the ligands around the chirality center. Okay, so now if I compare this one here, this configuration one versus this configuration two, are they the same? If I freeze these two compounds, I'm not doing any rotation. This is what I have, and this is what I have around the chirality center. Are they the same or different? They are different. They are different because the rotations of atoms in space around the chirality centers are different. Here, bromine is in bromine, for us, bromine is what? Across, you know. Like you're using the bromines, this is like a staggered, and this is like, this one is like a staggered, and this one is like what? A Clefson, you know. So they are different. But the name is what? The same. They are non-mirror images. So what's the relationship between them? What's the relationship between them? Are they the same enantiomers? Conformations? Things that we know. These two arrangements I have on the board. It wouldn't define anything that we know at this point here. They are not enantiomers because they are not mirror images. Number one, they are not mirror images. And they are not the same. That's because the BRs are same BRs here. And here that BRs are what? Across from each other. So there's something within this molecule, for instance, dipole-dipole repulsive forces are more in here than there. Dipole-dipole. You remember this from chapter 4? See, there's a delta negative here, and there's a delta negative there, isn't it? So that is my delta negative, and that's my delta negative, because this bromine is more electronegative than more carbon, so that is my delta negative. So here, the BRs are what? Going to do what? A repair. So there's more dipole-dipole interaction. Even though the name is the same, please, they are not cis and trans either, because there's no double bond. That's what I get a lot. But students say there's no cis and trans. No, there's no cis and trans here, because there's no double bond. Okay? So they are different. More dipole here. Very little dipole there is some in here, but it's more pronounced in this structure than it is in this structure here. Thank you very much. Okay. So many things. These two arrangements I have on the board are different. Okay. The relationship between 1 and 2. That's what we call they are diastereomers. Diastereomers. 1 and 2 are diastereomers. What are diastereomers? Non-mirror image stereomer isomers. Simple definition. Non-mirror image stereoisomers. I usually, on this level here, I need to go ahead and say non-mirror image stereoisomers with more than one chirality was center. That would suffice for us here. But it is such a big thing here. The compound necessarily doesn't have to have a chirality center. Even your geometric isomers, cis and trans, can be classified as what? Diastereomers. Because they are non-mirror image stereoisomers. So it's a very broad definition that I'm giving here for diastereomers. Non-mirror image stereoisomers. Sometimes with more than one chiral center, and sometimes there will be no chiral centers. But as you see on the board up here, these two things are stereoisomers. But they are non-mirror images. So that's what we mean by this. Diastereomers. Non-mirror image stereo isomers. So that's the stereoisomer. And by definition, you know what stereoisomers are. Isomers that differ only by the orientation of atoms in what? In space. So once you know stereoisomer and it is non-mirror image, it immediately becomes what? Diastereo. Okay. Good. But now, each one of these two diastereomers have chirality center. And so therefore we can do what? We can take what? A mirror what? Image of each one of them and create what? Enantiomers. See that? We can create enantiomers. So I'm taking a mirror image of this one here. That's my CH2, CH3, H here, and CH3 here, and Br here, and then Br there. Now, what's the relationship between 1 and 1A? That is what you test for your what? Super what? Imposability. Once you take a mirror image, you don't move on and say they are enantiomers. You test for their what? Super what? Imposability. If 1 and 1A are non-superimposable, then the relationship between them is that they are what? Enantiomers. Okay? So that is what this will show to you, this is exactly what I have on the board, is what this model is typifying. Green, green, blue, and blue. The top and the bottom are what? Different. So I'm going to superimpose. If I not go, doesn't match. This side is matching, but these here are not. Even if I do 180 degrees, and it's very important you do the 180 degrees. If I do 180 degrees, the top is different from what? The bottom, so I'm not going to have everything all aligned. The 180 is very, very important. You go 180, test forward. Stay the same and test forward. Do 180 and test forward. If you do both and you don't have all the atoms aligned, that means they are non-superimposable. They have chirality centers, and so therefore they are what? 1 and 1A are what? Enantiomers. 1 and 1A are enantiomers. Here the sizes are already different, so if I take a mirror image here, and I do the same thing here, the hydrogen is there, Br is here, hydrogen here, Br is there, got CH3 here, CH2, CH3 here. 2 and 2A are definitely going to be what? Enantiomers. So this compound, 2,3-dibromo-pentane, how many stereoisomers do I have on this compound? How many stereoisomers? 4. It has 4 stereoisomers. If it has 1 chirality center, I have 2 stereoisomers in it, 2 enantiomers. Now if I have 2 chirality centers, I have 4 enantiomers. Out of these enantiomers, 1 and 1A, out of these stereoisomers, 1 and 1A are enantiomers, 2 and 2A are what? Enantiomers. Any relationship between this group and that group are what? Any relationship between 1 and 1,2 diastereomer, 1 and 2A is also what? Diastereomer. 1A and 2 are also what? Diastereomer. And then 1A and also what? 2A are also what? Diastereomers. In a relationship of this group and that group is diastereomeric because they are not what? Mirror images. So that is what the concept of diastereomers are. And that goes a long way. There's so many diastereomer compounds up there. So the general rule here is that if I have the maximum number of stereoisomers that a compound can give me is 2 raised to the power n is equal to the maximum number of stereo isomers, where n is equal to the number of chirality centers. 2 raised to the power n will give me the maximum number of what? Stereoisomers, where n is equal to the number of chirality centers. This compound has 2 chirality centers, isn't it? 2 raised to the power 2 is equal to what? 4. Those are the 4 stereoisomers. Then when you draw, then we do the comparison. In the mirror image is enantiomers. Non-mirror images are what? Diastereomers. Okay? Diastereomers are, it's initially we established, unlike enantiomers, where physical and chemical properties are going to be what? The same. Everything's going to be the same, with the exception of what? Interaction with polarized what? Light. You have all that, isn't it? Enantiomers. Everything between them are going to be what? The same, with the exception of what? Interaction through a polarized light. Diastereomers, everything between them are going to be what? Different. You saw that. There's more dipole repulsive forces here than it is there. That is going to cause what? Physical properties to be what? Different. If the melting point, the way it's going to pack and all that is going to be different. So diastereomers have different what? Physical and chemical what? Properties. So let's make a know that here. Differentiate them immediately from what? Enantiomers. Different physical and chemical properties. Rotation polarized lines can be different or can be what? The same. You don't need to use that to test for diastereomeric. You got to use physical and chemical properties. Okay, good. Let's try another compound that also has what? 2 chirality centers. Okay. Let's do this. Let's take 2,3-dibromobutane. And let's create the same thing here. I'm going to just put a CH3 on the bottom here. CH3 here. I'm cheating a little bit here, but bear with me. Like I said, if you're using anything, then just put another page and then just look at it. But here I'm cheating a little bit. I'm doing 2,3-dibromo what? Butane. 2,3-dibromobutane also has 2 chirality centers, carbon 2 and 3 and chiral. If I set it up, that's my carbon 2 and it's my carbon 3. Carbon 2 is right there, has CH3, BRH, and then the rest of the molecule as you see it up there. So now we're going to test this, how many stereoisomers that we're going to have for this compound here.